the circuit where we have the active components, we have the filter and the amplifier. So this one is the combination of the amplifier and the filter. So filtering is done and the filter signal are then amplified, right? And for that we are using the operational amplifier, the op amp. So we have the second order circuit, and second order means here the filtering layers I'm talking about. We have the set of reactive components. Okay, so two sets of reactive components are there and that are connected in the Butterworth structure. Now, when we are saying Butterworth or any other type of filter, so many you know, right? So for that, it is decided on the basis of the response it is providing, right? So the Butterworth response, I guess it is known to you because you have already gone through those things in your basic electronics also. So the filter that will provide you that particular response will be the Butterworth filter. So here we are having the second order filter and we have the op amp to amplify the signal, and that will be your second order low pass Butterworth active filter. And then we cascade the structure with the same structure, so that will provide us the fourth order filter, right? So here, first of all, I'll show you the manual. You can have the snapshot of that, and it consists of the related mathematical models also, right? That will help you to design. The circuit is there and the expected response, right? So those things are here. Well, so yeah, I would like to show you the manual first of all.
Sir, excuse me, sir.
Yeah, sure.
Sir, if it is possible after the class, can you upload the hardware manuals of the previous experiments, sir?
Okay. At this moment, you please take the snapshot of this one. I'll try to upload. I guess it is visible.
Sir, it's visible, sir, but not clear, sir.
Okay. Please have a snapshot of this one so that at this moment you can at least, refer this one, that what you are doing actually. Okay, so this is the mathematical representation. Okay, then the next thing is the circuit what we are using here. So this is the circuit. You can see we have two cascaded structure. So the very elementary one, the basic one, this one I'm talking about. That means both, if I say like this is second order and this one is repeated here. So this is now total is the fourth order Butterworth low pass filter. Okay, you have already simulated this in the ComSim lab also, multi-sim lab also. We have to take these readings, we have to vary the frequency, and accordingly we'll have to calculate the response. And this is the expected response. Okay. We have the circuit setup. Microwave lab we have here. You are very much familiar with this board. So we have the function generator, you can see, right? This is the breadboard. We have the input setups here. You can see plus 12 volt, 5 volt ground and all those things. You are very much familiar with these things. You have completed so many experiments on this. So this is your micro lab kit on which we are going to design. Now this is your, if you see this particular portion, this one. So this is your second order Butterworth low pass filter. Now the same is implemented here also, and the cascaded structure of this one, this overall is your fourth order Butterworth low pass filter. You have the 741 operational amplifier here to amplify the output of the filter, right? So this is for second order, this is for the fourth order. So first of all, we'll try to take the input signal, then we'll get the output of the second order Butterworth, which will be input for the next layer, okay? And the output of this one will give you the output of the fourth order Butterworth low pass filter. Okay, so we have the structure. Actually, we have provided from here. This is the input section. The second order is this one, and fourth order is this one, and we will collect the output from here actually, because we are providing input from here. Excitation we are providing from here. Right. So we have provided the input. So I'll show you the input, then I'll show you the output of the second order, then I'll show you the output of the fourth order, like that. One by one.
First,
so yes.
First 100 hertz setting on
See.
252.
See, first you please see this reading. So as per the manual, we have arranged this. Wait a minute. I'm not sure whether you are able to see the reading or not. You can see 101.0 hertz, right? Here you
Sir,
can see it is mentioned.
A little bit away from the instrument, sir.
Is it okay now?
No, sir, a little bit more away from the instrument.
Yes, are you
sir.
able to see the display on the screen?
Sir, little bit at the top, sir. Yes, sir. Yes, sir.
Okay. So it is, we have to set at 101 or 100 hertz. Little bit fluctuation is there. Okay. So this is the frequency we have set here. Input voltage. And now we are going to show you the, and 2 volt input is there. That we can see, the plot of this one we can see on the CR.
1 division 2 volt.
Yes. You can see Mandal sir is showing the division per volt also, right? That is required to measure the value in this scale, right?
Yeah.
You can see. Voltage per division you can see, right? 2 volt peak to peak we want. Okay, so it is showing 2 here. See, it is showing 2 here. Okay, however, this reading is showing in the time domain. So from here also you can calculate the frequency. You know, CRO is always showing the reading in the time domain. So time versus magnitude. But here you can see the exact frequency, how much you have set. So this input is actually showing here in the graphical form in this CRO. So we have provided this as input, right? So this is the input we have provided from here. You can see we have provided from here. So this is the CRO where is going, right? So the same thing is showing in the CRO. This input is coming, and we have provided this. Yeah, and we have provided this. You can see we have this arrangement. You can see. So the same we are taking this one. Yes, this is the ground. Same we are collecting here to show you here on the CRO, and we are providing the input to. This is the input. Okay, input wire you can see it is going this blue one. Okay, so we have provided this as input. Right, you can see. Now I would like to show you the circuit once again so that you can understand. Please have a look on this and take a snapshot of this. So yes, we have to provide input. We have to provide input to this resistance. See, this is this resistance. We have to provide input to this resistance, right? This resistance, input resistance is there, right? Of kitna hai ye?
ये 10 के क्या है?
100 hertz input we are providing. Okay, 2 pp, 2 volt peak to peak we have set, and 10 kilo ohm का भी use किया ना? 10 kilo ohm. All the resistance are of value 10 kilo ohm. 10 kilo ohm resistance we have used, right? So we have provided input to this one. So this is the same 10 kilo ohm resistance here. To this blue wire is carrying the input. Okay, 2 volt peak to peak at 100 hertz. We have provided this input. Okay, then
अब ये है
now see, please concentrate on this.
नंबर 3 आपका ये आउटपुट आएगा आपका, ये 4 वोल्ट हो गया यार, 2 डिविजन्स.
Okay,
2 डिविजन्स.
now see, reading you can see, and is still at 2 volt peak to peak, right? So we have 4 volt actually.
4 डिविजन्स.
2 divisions we have, no? 2 volt per division, 2 division 1 and 2. So 4 volt we have. Why? Because the signal have amplified by the op amp. We are collecting this output from op amp. Okay, this is the output of the second order filter. Okay, and pin number 6 we have used to collect the output. You can see, you know that thing from op amp, right? Yes. So this is the pin number 6. Okay. Then now
ये fourth order.
This was the second order output we have seen just now. This is the second order output. Now this is the fourth order. Now we are going to see the fourth order.
8 voltage.
Now see, again is going to be amplified, and now we have 8 volt peak to peak. So 2 volt per division, and we have 1, 2, 3, 4 blocks, right? So 8 volt, 2 volt per division into 4 divisions. So 8 volt peak to peak we are having. This is the output of the fourth order Butterworth low pass filter. You can have a snap of it. And please take the snap of the circuit. Snapshot of this one. Right? Now we are going to change the input. Previously it was 100 hertz. Now we are making it 300 hertz. We are going to change the frequency, okay? Yes, so we have tried to set at 300. We are getting 309 because it is fluctuating. So it's okay. 309, no much variation, 309, okay? At 309, again, the same voltage we have, there's no variation in the voltage. It is still 2 volt, right? It's still 2 volt. And we are going to see the output. So this is, you can see, yes, 6 numbers. Okay?
6 numbers.
Okay, so this is the output of the second order filter. Still, you can see the same voltage because we have not changed the voltage, the frequency have only changed, right? So we have still 4 volt output. And now if you see at fourth order, we still have the 8 volt. Only there is a variation in the time period because we have changed the input. Now we'll make it at 500 hertz. Okay, we are going to change the frequency and we'll see the reading at 500 hertz. Oh, 500.
ये आप किलो में जाएगा वैसे वैसे आपका
थोड़ा दिक्कत होता है बस ठीक है बस चलेगा okay so now we are going to check it is a filter right so for filter the most important criteria is the parameters the frequency so that's why we are changing the frequency the magnitude is not going to change it is still same so input signal only we are changing right so we can see that it have allowed the 100 hertz it have allowed 300 hertz now it is allowing 500 hertz also right and the same voltage so you can see output of the second order So why we are doing this? Because we know that this low pass filter allow all the signals up to the cutoff frequency, right? And we are in the process to determine the cutoff frequency of this filter, right? So it have allowed the 500 hertz signal also, right? This is the output of the fourth order. Now we'll check for the sixth order. See, this is the output for the sixth order. It allows all the 8 volt to pass, right? Amplified version. So that means it have allowed the 500 hertz also. हाँ बढ़ा दीजिए आपको 10 किलोहर्ट्ज के बाद में 15 तक फ्रीक्वेंसी मिल जाएगा. So 10 kilohertz में देख लेते हैं. 10 kilohertz. Now we are going to see 10 kilohertz because the expected cutoff frequency is 15 kilohertz. So we'll check at 10 kilohertz if it will allow to 10 kilohertz. It will allow the below frequencies also.
कम होते जा रहा है बोलते या 400 ये है ना किलोहर्ट्ज पर अभी फिक्स है इतना पर अभी फिक्स है वोल्टेज उसके बाद जैसे ये कम करते जाएंगे ना फ्रीक्वेंसी बढ़ाते जाएंगे ये एम्पलीट्यूड कम होते जा रहा है तो वही जहां पर कम हो ना वो दिखा दीजिए ये कम हो रहा है 6.42 पे मत रखिए 4 किलोहर्ट्ज पे पर कर दीजिए ओके ठीक है सो नाउ 4 से भी थोड़ा कम हुआ है फिर 2 किलोहर्ट्ज दिखाइए 2 kilohertz पे okay now we can see the output sixth order output at 2 kilohertz we can see that it have allowed the 8 volt to pass right 8 volt to pass and उसको देखने के लिए since we have improved the frequency so time per division हमने थोड़ा सा बढ़ा दिया है ताकि हमको better view मिले so we can see that it have allowed 2 kilohertz to pass now we'll slowly improve the frequency increase the frequency we will try to see the change okay so now we are going to increase the frequency a little bit slowly थोड़ा सा बढ़ाइए उसको 4 किलोहर्ट्ज तक लाइए फोर्थ ऑर्डर का देख रहा है फोर्थ का नहीं देख रहा है सिक्स का ही देख रहा है सिक्स ऑर्डर सॉरी सिक्स नहीं तो क्या फोर्थ एंड ये सेकंड ऑर्डर एंड फोर्थ ऑर्डर है ना हाँ फोर्थ ऑर्डर का देख रहा है फोर्थ ऑर्डर का ठीक उसको बढ़ाइए सब थोड़ा और बढ़ाइए नहीं बढ़ाना 6 से 7 8 ऐसे लिखिए okay बस छोड़ दीजिए now we can see the deterioration in the amplitude right previously it have covered 4 blocks now we can see that it is covering less than that why because slowly we have reached the cutoff frequency and cutoff frequency now we are checking it at 7 gigahertz okay 7 kilohertz अभी हम थोड़ा सा जाएंगे 5 किलोहर्ट्ज पे 5 किलोहर्ट्ज पे चेक कीजिए सर एकदम 5 किलोहर्ट्ज पे देखो 5 किलोहर्ट्ज पे अलाउ 8 वोल्ट पीक टू पीक कोई प्रॉब्लम नहीं है 5 से भी 6 पे आते हम लोग 6 पे हाँ 6 पे आइए ओके हाँ अभी देखो थोड़ा डिटोरिएशन आप महसूस करोगे ब्लॉक लाइन से थोड़ा नीचे हो गया है और अब हम 7 किलोहर्ट्ज पे जाते हैं अभी देखो आपको पूरा क्लियर पता चल रहा है एम्पलीट्यूड डिटोरिएशन है ना इससे पता चलता है कि आवर कट ऑफ फ्रीक्वेंसी इज इन बिटवीन 6 to 7 it is slowly deteriorating right so cut off frequency is in between 6 to 7 kilohertz now slowly when we increase the frequency so definitely it will not allow the overall signal to pass and it will slowly the amplitude will deteriorate okay हाँ और कम कीजिए 10 पे कर दीजिए सर Now at 10 kilohertz, you can see that it have allowed only half of the signal to pass, right? We are checking the fourth order response. So we can say that we are right that this cutoff frequency is in between 6 to 7, roughly 6.5 kilohertz. After that, we have obtained the deterioration in the magnitude. So the cutoff frequency for the low pass Butterworth filter is 6.5 kilohertz roughly. Okay. Any query? Please let me know if you have. Neela ma'am? Hello, Neela ma'am? Am I audible?
Fourth order.
Yes, ma'am.
Second
Yes,
order
ma'am.
and fourth order Butterworth filter, they will have to plot the graph also, na?
Yes, ma'am. Yes,
Or
ma'am.
not? Because reading to nahi le pa raha hai, how they will plot?
They can take the snapshot of the reading. I'm continuously showing them the reading. They can take the snapshot.
Okay.
I'll once again show them 3 or 4 readings so that they can take the snapshot and accordingly they can write. Yes, in the assignment, actually, I have given the link for the assignment for 3 experiments. So you can, ma'am, already 3 assignment link I have given for hardware and software, and they can use that link. Yes.
They can use it that. Otherwise, they will have to submit it in the combined folder. If separate assignment, then no problem. Whatever, because if suppose they will submit in a folder 5 experiment, they will merge in PDF format and then one by one they can submit in folder. Otherwise they can submit it at assignment. एक ही लेकिन करे किसमें करना Dr. GK Mishra, you also suggest.
Okay, I'll inform them. Okay, students, don't right now if you have already submitted, then there is no issue. If you have not yet submitted, please wait. We'll discuss and let you know. Okay.
Yes.
It's a matter of just generating one link. I'll generate that. So I'll discuss and then accordingly we'll let you know. Okay, don't worry. So if you have not yet submitted, wait. But you please write and have copy with you,
ready.
and whenever they'll provide you the instruction, you accordingly submit.
Yes, be ready with your write-up.
Okay, so now I'm going to show you 5 readings. Okay, and please have a snapshot of that. That will help you to to write the journal. So थोड़ा सा ना एक बार पीछे कर दीजिए वापस से. I'll show you the reading at 500 hertz. 500 hertz पर plus set कीजिएगा. 4 or 5 reading I'm going to give you. Please have a snapshot of that. 500 hertz, 200 to 500 to okay. See, this is your 500 hertz input. Okay, 500 hertz input, and this is the 4th order reading at 500 hertz. 4th order reading at 500 hertz. You can have a snapshot of this. 1 kilohertz.
Sir.
Yes.
Sir, in the snapshot, the graph is not, it's not clear, sir, actually, because of the light there.
Okay, wait a minute. I am trying to fix it. Is it okay now?
Yes, sir.
You want shadow or what? You want shadow?
No, sir, when we are taking screenshot, sir, it's not clear
is
actually.
It okay now? Okay, now please see. Check. Is it okay?
Yes, sir.
Okay, please have snapshot of this. It is at 2 volt peak to peak value. Okay, 2 volt peak to peak. So this is the terminal setting. Please take snapshot of this one also. It will help you to understand the scale value. Okay, this reading is for 500 hertz. Sir, 1 kilohertz पर दिखा दीजिए.
Sir, for second order, fourth order, sir.
This is for 4th order.
Yes.
Second order पे भी लगा दीजिए. Okay, I'll show you for second order also. 500 पहले second और fourth पे ना alternately. तो 500 पे set कर लीजिए. Fast. This is now what I am the previous reading what I have shown you, it was for 500 hertz 4th order. Now what I am showing you, it is 500 hertz second order. 2 volt peak to peak. I hope you have taken the snap. Now we are going to check 1 kilohertz. 1 kilohertz second order. This is 1 kilohertz second order. Fourth order में fourth order. 1 kilohertz fourth order. This is for 1 kilohertz fourth order. Now we'll check 5 kilohertz. This is 5 kilohertz second order. 5 kilohertz second order.
Sir, could you move the phone a little bit downwards? Yes.
Okay, this is 5 kilohertz second order. Please wait a minute. I'm going to change the times per division also. It will give you a better picture. Okay, so I have changed the scale value. 0.2 per division है 0.2 millisecond. नहीं, it's 0.2 millisecond. 0.2 second में आएगा. ये millisecond. So 0.2 millisecond is there. Okay, so the conversion value will give you the same frequency. इस पे check कितना frequency पे 5 kilohertz. 5 kilohertz second order. Okay, fourth order दिखा. Now this is 5 kilohertz fourth order. 5 kilohertz fourth order. Now we know that the cutoff frequency is 6.5 kilohertz, so we'll check at 6.5 kilohertz. Six point five तो बढ़ गया ना 6.5. 6.5 और थोड़ा पीछे जाइए. सेकेंड ऑर्डर पे लगा दीजिए. So this is second order 6.5 kilohertz, which is the cutoff frequency. Okay, 6.5 kilohertz second order. This is the cutoff frequency. And now I'm going to show you fourth order. So this is the fourth order, 6.5 kilohertz, which is the cutoff frequency. Fourth order. Now we'll check at 7 kilohertz. Not 7 kilohertz, 8 kilohertz we'll check. Because 7 kilohertz, the deviation will be very small. So we'll check at 8 kilohertz. चलेगा सेकेंड ऑर्डर में लगाए हैं. डेविएशन बहुत कम 10 8.10. अच्छा 9 किलोवाट से 9 किलोवाट बस 9 पे लगे 9.5 9. Okay. Now you can see the deviation. You can easily you can observe. So this is at 9 kilohertz second order. 9 kilohertz second order. Deviation you can see, right? The amplitude deviation you can see. 9 kilohertz second order. And now we are going to see 9 kilohertz fourth order. fourth order में लगा दीजिए sir. Now, good amount of deviation here you can see because it is the fourth order will give you the better picture. So this is the 9 kilohertz fourth order. 9 kilohertz fourth order. Previously it have covered 4 blocks. Now it is covering only 2 blocks, right? 10 kilohertz now we'll check. So 10 kilohertz second order लगा दीजिए. Second order. So this is the 10 kilohertz second order. You can see in the second order also you can easily see the change. Previously it was covering 2 blocks. Now it is covering nearly 1.5 block. 10 kilohertz second order. Now if we see for the fourth order, obviously deviation will be more. So more deteriorated output. Now it is covering only 2 blocks, right? It is the 10 kilohertz fourth order. 10 kilohertz fourth order. So this way we can see the deviation. Okay, after 6.5, the filter is not allowed the overall signal to pass, and so we have deterioration in the output, right? So this way we have completed our second and fourth order experiment. If you have any query, please ask. My microphone was actually, it was in the mute form. So once again, I'd like to show you. You have a good idea how to draw the response. So this is the frequency domain response. Okay. So it have to be drawn over the semi-log paper. So you have to take the dB value or logarithmic value of the magnitude, and with variation in the frequency you have to plot, right? So you have to calculate the bandwidth also. You know, for the bandpass filter it have to be difference between the lower cutoff and upper cutoff. Now it is the low pass filter, so you have only one cutoff. So bandwidth will be from 0 to the cutoff value. That will be the bandwidth. So you can see the plot. I guess it is visible. The second order and the fourth order you can easily see, right? So so you will have to make the plot, and then you will have to draw a minus 3 dB line. Minus 3 dB means what? 3 dB below the peak value. This is the peak value. So 3 dB below the peak value. This will give you the bandwidth, right, for the fourth order and for the second order respectively, right? So you have to make the plot, then below the peak value 3 dB below line you will have to draw, and this will give you the bandwidth for fourth order and for the second order. So likewise you have to draw. Okay,
sir, excuse me,
is
sir.
it okay? Yes,
Sir, we took the screenshot, sir, but the units on that screen would not be visible from that, sir. You please provide us the data of x-axis and y-axis, sir.
Unit means time per division you are talking about, or
no,
sir. Voltage per division,
sir.
right?
That, sir, if you see the CRO screen, sir. So sir, how much?
Okay, I'm telling you. Yeah, I'm telling you. It will be helpful for you. I can say that input will be 2 volt peak to peak always. Okay, 2 volt peak to peak, and so it have maintained that particular value. We have not changed the scaled value. So you have the snapshot. So just by counting the blocks, you can say what is the output value.
because we have changed the time per division. We have not changed the voltage per division. It was 2 volt peak to peak that time also, and even now also it is at 2 volt peak to peak, right? So don't worry, you keep it as 2 volt peak to peak. Here you can see still at 2 volt peak to peak. Here it is 2 volt peak to peak. So, 2 volt peak to peak, right? So you have the blocks, you have to multiply this by 2, so it will give you the voltage value. Okay, about the frequency, so previously we have taken at 1 volt पे लिए थे, जो पहले था, अभी तो 0.21. Okay, so previously it was at 0.5 millisecond. Okay, and after the cutoff, we have taken at 0.2 millisecond. Previously it was 0.5 millisecond. After cutoff, that is 6.5, we have taken at 0.2 milliseconds. So only one change in scale value was there. So likewise you can calculate. Okay, is it okay? Any query? Well, so if you don't have any query, I guess we can go ahead with the next experiment. And this is the observation table I would like to show that will help you when you will make the plot. Please have a snapshot of this. Okay, so now we are going for the next experiment.
Hello. Students, you will have to, if you are going to plot the response on the same curve, what is the significance? What is the difference in the response? What does it basically indicate? Once you increase the order, second order, fourth order, so whatever may be the role of, and whether it is closer to the ideal response or not, you will have to see. So the objective of the experiment is that you will have to compare the significance of order, higher order, lower order of the filter. What does it actually mean? So first you see the ideal response. It is flat. Then second order, fourth order, what is the response? Okay, so you will have to find out some conclusion of your own. Why you are doing what Dr. G.K. Mishra has explained so nicely, what conclusion you are getting. Okay. Okay, Dr. G.K. Mishra. Okay.
Now we are going to start the next experiment, signal sampling and reconstruction. And this also we have completed there in the simulation lab. You have a good idea about the signal sampling. And you know here the Nyquist criteria should be satisfied, right? Nyquist criteria means, you know, the sampling frequency should be twice to that of the maximum frequency component of the master signal, because the master signal may have number of frequency component. So you will have to identify the maximum frequency component, and the sampling frequency should be twice to that of the maximum frequency component or more than that. Okay. If you talk about the time domains, obviously the maximum frequency component will have minimum time period, right? So then the sampling signals time period should be half to that of the minimum period of the signal component. Okay, that is the Nyquist criteria. And if Nyquist criteria will not be satisfied, then you know aliasing effect will take place and you will not be able to reconstruct the signal back, right? Correct signal you cannot be able to collect back, right? So that's why this Nyquist criteria should be satisfied. And we have 3 sampling schemes here. We'll check for all of them. The natural sampling, the flat top sampling, and the sample circuit is there. And then sample and hold circuit, right? and then we'll reconstruct the sampled signal, all the three sampled signals, three different means we have, but by the help of the whole circuit, that is nothing but the integrator. We required actually a simple capacitor, and you know the envelope detector, right? Same concept is applied here because we have the capacitor. So capacitor will get charged up to the peak value and then slowly discharge until you will have the next excitation. Okay, so likewise it will connect the line between the two pulses by charging and discharging, and we'll have a continuous signal, right? So for that we require the time constant value to be adjusted correctively. Time constant is what? The product of R and C. That means how much time it will take to charge and how much time it will take to discharge. That should be adjusted. And then we can reconstruct the signal back. So this is known as, this combination is known as, the circuit combination is known as integrator circuit. And integrator circuit is nothing. It is a low pass filter only. So it means what? Your cutoff frequency of the low pass filter should be little bit greater than the maximum frequency component of the master signal, because you want all the signals to pass, only the master signal to pass, right? So that means that the filter should allow the master signal to pass, and that's why the cutoff frequency of the low pass filter should be slightly greater than the maximum frequency component of the master signal. So this concept we'll use here to generate the signal back from the sampled version of the signal, that is from the discrete signal to the continuous signal. So first we'll convert the continuous signal to discrete one by the help of the sampling, and then from the discrete to the continuous one by the help of the reconstruction circuit or the whole circuits. So this is the manual. Yeah, I suggest you to take the snapshot of this one for your reference. इसको जब आप जूम इन करेंगे तो आप इसको पढ़ भी सकते हैं. And this is the block we are going to use for our purpose. This is the arrangement we are going to use for our purpose. So you are very much familiar with the system because we have discussed number of times. We have the function generator here. Okay, this function generator can provide you signal from 1 kilohertz to 2 kilohertz. So 1 kilohertz selection line and 2 kilohertz selection line is there. We have the buffer. We have the natural sampling block that will provide you the natural sampling. Okay. And after sampling, if you want to reconstruct the signal back, you should have a filter, that is the integrator circuit. Okay. This is the clock. This will help you to generate the sampled signal. So what actually we are doing when we are doing the sampling, what we are actually doing, we multiply, okay, we multiply the massive signal with the train of impulse. Train of impulse क्या है? Train of impulse means impulse signal आपको पता है that will generate at a particular instant of time. तो आप एक पर्टिकुलर पीरियड के बाद एक इंपल्स देते हो. इंपल्स मतलब जब आप एक्साइटेशन दोगे सिर्फ तभी वो एग्जिस्ट करेगा. ठीक है, आप इसे टच करोगे सिग्नल आएगा, आप उंगली हटा लोगे सिग्नल चला जाएगा. तो दैट इज द इंपल्स. For that particular duration of time it will appear. So on periodic manner you will generate that signal. So the signal intensity will be at that point of time only, and for rest of the place it will have zero value. So when you will multiply this train of impulse with the massive signal, so only for that instant of time the signal will be taken, and for rest of the time signal will not be taken, right? So we will have and this impulse signal will have unit amplitude. So when you will multiply the unit amplitude signal with your massive signal, so unit amplitude into intensity of the massive signal, say 5 volt or 6 volt something, so that will be multiplied, right? So you will have the signal component at that instant of time only, and for rest of the duration you will have zero value. So that is actually the concept behind the sampling. Okay, and this period is the sampling period. That is the duration between the two impulses are the period, because it is a periodic one, and this is known as the sampling period. So sampling period should be half
or less than that to that of the minimum period component of the message signal. In terms of frequency, it is obviously inverse of that. So sampling frequency should be twice to that of the maximum frequency component of the message signal, right? So this is for the block structure, block diagram for the natural sampling. Please have a snapshot of this. Next, we have the same setup, but here we'll use the sample and hold structure. Again, please take a snapshot of this. And at last, we'll have the flat top sampled version, flat top sampled. So what type of sampling scheme we are taking? We'll just change the block here. Rest of the thing is going to be same. Rest of the thing is you just have the signal, and here it will multiply the signal with the controlled clock. That will give you the train of impulse. And this is the expected plot. You can see the 1 kilohertz input signal. This is the output of the sampling circuit. This is the output of the natural sampling. And this is the output of the reconstructed signal. Reconstructed signal. So this is for the natural sampling. This is the train of impulse. Okay, so when it will be multiplied with this one, you will have this output. And this is the reconstructed one. When it will pass through the low pass filter, you will have this output. Likewise, here you can see this one for sample and hold circuit. This is the control signal for sample and hold circuit. And when it will pass through the low pass filter, you will have this output. And this is for the flat top sampling input. And this is the output of the flat top sampling. So top is flat, you can see the top is flat. Here the top is not flat always. Here see the top is not flat. Here also the top is not flat. But here the top is always flat. That's why the name flat top sampling. And this is the reconstructed signal using the low pass filter. So now we are going to see the actual setup and the output. Please see the circuit here first and have a snapshot of this one. Here you can see that we have the input lines, we have the buffer. This block is for sample and hold circuit. This block is for sample and hold circuit. This one for flat top sampling. So we'll provide input here for sample and hold. We'll provide input here for flat top sampling, and we'll provide input here for natural sampling. Okay. And when we provide input here, so output line internally connected to the second order low pass Butterworth filter, that is nothing but the integrator. So here it will provide us the constructed signal, right? Now, this is the input. You can see, please have a look on this. It is a 2 kilohertz, 1.92 kilohertz. That means 2 kilohertz input we have provided. Amplitude is 2.57. You can see, which is written here. You can read and you can see on the plot also. Please have snapshot of this one at this moment only. This is the input we are going to provide. This is the continuous signal of 2 kilohertz frequency and amplitude 2.46 volt. Right? Now, we'll see the output of this. This is the input we have provided, right? And now we'll see the output of sample and hold. Okay. So now setting also we should check.
the function generator setup value, right? And you can see this is the clock value we have set. Okay, internal clock is there, is the external clock. This is external clock, this is internal clock. So we have provided the internal clock. You can see the switch. Internal clock value is there, right? And we have provided input from 2 kilohertz. You can see here 2 kilohertz, and here it is 1 kilohertz. It is written here. I guess it is visible. 1 kilohertz and 2 kilohertz. So we have provided input from 2 kilohertz, right? So 2 kilohertz input is provided, and the output of the output is sample and hold का दिखा रहे ना sir? नहीं, ये आपको clock का है. Clock, okay, clock value दिखिए sir. So this is the clock value. This is what? This gives you the sampling period. Okay, sampling period. So sampling period, you can see sampling period or sampling frequency. So I told you that sampling frequency should be greater than 2 times to that of the massive signal frequency. Massive signal frequency is 2 kilohertz. So it have to be more than 4 kilohertz. 4 kilohertz or more than that, 2 times to that of the massive signal. So you can see it is 7.68 kilohertz. It is good. The minimum possible value for this one should be 4 kilohertz as per the Nyquist criteria. Voltage is not so important here. However, we should take the reading. So voltage is 6.6 and you can see the frequency is 7.68 kilohertz. So it is satisfying the Nyquist criteria. Please have a snapshot of this one quickly. Okay, I guess you have taken the snapshot. Now we'll see the output of the sample and hold circuit. So this is the arrangement. Please have a snapshot of this. And this is the output of sample and hold circuit. Okay, let's go stop. Okay, so you can see the frequency is 1.92 kilohertz. It have not changed, right? Please take the snapshot of this one. This is the output of the sample and hold circuit. Manual. I'll show you the output, what is mentioned there in the manual also. So this is the output which is given here in the manual for sample and hold circuit. Right, sample and hold circuit. You can see similar type of output we are getting here. क्या बोल रहे हैं सर? ठीक है, 2 वोल्ट हम लोग 2 हर्ट्ज किलो हर्ट्ज दिए थे ना इसीलिए. Right, so please have a snapshot of this. Now we'll check the reconstructed signal. For that we'll have to take reading from the filter, second order filter. See, we are now getting reading from this second order filter. Okay, we are going to collect the reading from second order filter. So this is the output. We have reconstructed the signal back from the sampled one. Right? You can see the frequency 1.92 kilohertz still. So we have successfully reconstructed our signal back from the discrete signal because it has satisfied the Nyquist criteria. And this is what's shown in the manual. We have got the better reading because here the sinusoidal signal is not so clear, but we have got a better reading here. So please have a snapshot of this, all of you. Harshvardhan, is it visible?
Yes, sir.
Okay. All of you, please.
Sir, little bit right side readings once. Yes.
Is it okay now? It is 1.92 kilohertz, 2.49 volt. Okay. Now we are going to see the same input if we provide we'll use the natural sampling, right? So it should have this type of output, natural sampling. So let's check what we are getting. So now we are going to collect reading from the natural sampling. You can see this is the natural sampling section. It is mentioned here. Please have a snapshot of this. Natural sampling section for the same input. And this is the output what we are getting. Please have a snapshot of this. This is the output of the natural sampling. Here the tops are not flat, you can see. Right, tops are not flat. This is natural sampling. Here we have just multiplied the signal with the train of impulse. That's all. No signal conditioning is done. Please have a snapshot of this. And now I will try to reconstruct the signal back. For that, we'll apply the same low pass filter second order, which is an integrator only. Second order. Time partition change. Okay, so this is the expected reconstructed signal. You can see this is also not so good, right? From deviation, you can see it is not a smooth curve of sinus, but showing the sinusoidal nature. So we have this output. So बढ़ाना ही पड़ेगा. Amplitude. Okay, so this is the reconstructed signal. We can see it is not so smooth, right? But it is showing the sinusoidal behavior. So we can see that the output of the natural sampling section using the low pass filter is not so clear, not so good as compared to the sample and hold what we have seen in the previous case. Okay. Anyhow, please take the reading. It is 1.92 kilohertz at 1.44 volt, right?
Sir, could you hold the camera a little bit back and towards the right?
Okay, clear? Better?
Yes.
Okay, now we are going to see the last one, that is the flat top sampling. Your expected plot will show you the flat surface, right? And it is the most beautiful and clear output possible. Okay, possible clear output expected to be. So this is the expected output. So we are going to collect from flat top section. Please see, this is your flat top section, flat top. Please have a snapshot of this also. And here we have our sampled output. You can see here the tops are flat actually. In the previous case, the tops are not flat. Here all the tops are flat. So this is your flat top sampling. It is again 1.92 kilohertz and peak to peak value is 2.49 volt. Right. Now we'll see the appearance of the reconstructed signal. It is the expected plot. And now see what we are getting here. Okay, so this is the reconstructed signal, the continuous signal from the discrete one, 1.92 kilohertz, 1.49 volt, and if we compare, we found that the best reconstructed signal will have from the sample and hold circuit, then flat top, and at last the worst is given by the natural sampling, right? Because this output is better than your flat top, the natural one. However, if we use the fourth order, then expected plot will be, will have a better plot that is expected. So we'll check for fourth order also. Because if we, if filtering value will improve, then definitely see, this is the output of the fourth order. And that's why, because one more layer of filtering we have applied, one more capacitive behavior we have added, right? So you can see the obvious, it was expected that we have a better output, right? The reconstructed signal. So this is the output of the fourth order low pass butterworth filter. So for all the cases, we'll have this output, the better output. Okay. So that's all about the sample and hold circuit. If you have any query, please ask. Or if you want any support, please let me know what I can do for you. I've shown you the plot, I've shown you the setup, the manual also I've shown you. If you want anything else, please let me know. Yeah. Now we are moving towards the TDM, time division multiplexing, TDM experiment. But in between, if you have to discuss anything, if you want, please let me know. I'm here for you. Good idea about the time division multiplexing, I know. Here we have say more than one channel, okay, and we can send the signal from all the channels to the time division multiplexer, and time division multiplexer will provide, it is like, switch. So if suppose m number of channels are there, input channels are there, and n number of output channels are there, so a particular mth channel will provide signal to some nth channel, okay, some ith channel will provide signal to some jth channel, something like that. So this connection, okay, will be there for particular duration of time, okay. Slot wise, it will allow all the channels to provide its signal, and then it will be disconnected, right? बहुत सारा ब्रांच है, हर ब्रांच को एक बार मौका मिलता है अपना सिग्नल को पास ऑन करने का, और फिर वो स्विच ऑफ हो जाता है और फिर मौका दूसरे चैनल को मिलता है. So that is the time division multiplexing. On the basis of the time, the time slot is allocated to all the channels, okay, and the channel will be allowed to send the signal at the prescribed duration of time. So that is the time division multiplexing, okay. There is a control line that will decide that the chance will be given to whom. So it is pre-decided. We have the synchronous and the asynchronous mode. In the synchronous mode, all the channels will have the equal time duration to provide the signal. In the asynchronous one, it is unequal. It depends on the application. So here in the lab, we are using the synchronous time division multiplexing. We'll use the 4-channel system. So you can see that we have provided input from all the 4 lines, right? And we'll have output, and those outputs are not interfering with each other. However, the input is provided at the same frequency, but even though there will be no interference, because the TDM system will keep track that at any instant of time, only one signal should be allowed to pass. So what we'll do, we'll provide input, okay? 4 input line will be there, and the combined signal will be provided to the demultiplexer. Now the demultiplexer will again divide the combined signal, the composite signal, because those are arranged on the time slot basis, right? Like for time slot A, signal channel A will appear, then time slot B, signal channel B will appear, like that. And then at the demodulator section, it will be arranged by the demodulator and will have all the 4 separate signals, right? Without any disturbance, without any interference. So that is your 4-channel multiplexing demultiplexing system, TDM system. This is the block diagram what we are going to use for the experiment. So you can see that we have the function generator and we have 4 lines, 1, 2, 3, 4. Okay. We can use same frequency also, but here in the lab we have options. So we are providing different frequencies, 250 Hertz, 500 Hertz, 1 kilohertz and 2 kilohertz. And those signals are provided to this multiplexer. Okay. Then the combined signal will go from the multiplexer to the demultiplexer. The demultiplexer is capable to separate the signals into again channel number 0, like here channel number 0, 1, 2, 3. So channel number 0, 1, 2, 3. And we have the filter here. So on the basis of this cutoff frequency, we have the band pass filter basically. This filter is the band pass filter, because if we use the low pass filter, then the signal that will allow 500 Hertz will also allow 250 Hertz to pass. If you use the low pass filter or the high pass filter, then if the signal will allow 500 Hertz, it will allow 1 kilohertz also. So we should have the band pass filter that will allow only particular signal band. That means if we have the cutoff frequency, say 500 to 1 kilohertz, so it will allow only this particular portion to pass, right? So that's why we have 4 different filters, right? So this filter will allow only particular signal component to pass, 1, 2, 3, 4, right? And we have this signal, input signal back at this end. So here the synchronization is required. So for the synchronization purpose, common clock is used to control the multiplexer and the demultiplexer also, because you know that time slot is given. So time slot means it will be operated on the basis of control that is provided by the clock. So common clock is used here. That is shown here. This is the clock for the multiplexer. This is for the demultiplexer. Okay. So please have a snapshot of this first. विभाजी, good afternoon.
Good afternoon, sir.
अभी हम लोग TDM सिस्टम डिस्कस कर रहे हैं. इसके बाद स्टूडेंट जो है ना वो सिमुलेशन लैब जो है वो ज्वाइन करेंगे.
हाँ.
तो वही नीला आपको बोलिए उनको सिस्टम थोड़ा उनको प्रोवाइड कर दीजिएगा.
हाँ सर, सिस्टम मेरा रेडी है.
Okay, students, please have a snapshot of this block diagram. And now I would like to show you the setup. So you can see here, I guess it is difficult for you to read, but I will try. Here we have, you can see 250 kilohertz, sorry, 250 hertz, 500 hertz, 1 kilohertz, and more in here, and 2 kilohertz. 2 kilohertz. 4 input lines are there. Please wait a minute. Okay. So we have 4 input lines, right? You can see, and we have the lines that is passing through this channel number 0, 1, 2, and 3. These are the inputs for the time region multiplexer. Then the combined output will be provided by the multiplexer here that we'll see. We'll have the combined output separated on the basis of the time slot. Okay, so for first duration, we will show you the first channel output, the second channel, third channel, fourth channel, then again first channel, second channel, like that it will provide the as the output. That thing is accepted by this demultiplexer section. So this is the output from multiplexer, it is going to the input of the demultiplexer. And then you have the filter. You can see this is the filter, band pass filter you have, band pass filter. Okay, 4 band pass filter. And the 4 output of this band pass filter will give you the 0, 1, 2, 3 channel, which is the input you have provided accordingly, right? So we'll see all of them. So ये सर जो है, so see this is now, please take the snapshot. This is the channel number 0, 250 hertz input. Please have snapshot.
Sir, little bit at the top. Yes, sir, it's visible.
Okay. Yes, sir. So this is 500 hertz input. 500 hertz input. Channel number 1. I guess you have taken the snapshot. Now,
Yes.
This is your 1 kilohertz. One kilohertz input. Channel number 2. We have channel number 0, channel number 1, and this is channel number 2. And this is 2 kilohertz. 5.7 volt सब में semi है ना volt, so 5.7 volt. Channel number 3. Okay, channel number 3. So all these inputs are now going to pass through the multiplexer. Okay, and we have the multiplexer output. And this is the multiplexer output. This is the most important one. So this is the combined form of all the inputs. Okay, on the time slot basis. Time period slot कम कीजिएगा sir. हाँ, बस ठीक है. This particular slot, if you see, it is carrying the channel number, the output of what you have seen, all the 4 inputs, channel number 0, 1, 2, 3. All the inputs are here, right? In the combined form. Right, so this is the magnified look. So this actually is the output of the multiplexer, where on the time slot basis we have channel number 0 output, then channel number 1 output, then 2, and then 3. Okay, and this is the input for the demultiplexer. Please have a snapshot of this. Now the same is the input. Now I'm showing you the input for the demultiplexer. So actually it is same, because the same thing is going to demultiplexer. So the previous was the output of the multiplexer, and this one is the input for the demultiplexer. Both are same. Please have a snapshot of this also. And now I would like to show you the output of channel number 0 at the demultiplexer. So this is the output for the channel number 0 of the demultiplexer, the 250 hertz, which is actually 240 hertz. Input was also 240 hertz, but it was set here as 250. That's why I'm saying 250. So it is same as your input. If you have an input plot, you can compare. You can see that both are same. Okay. Likewise, this is the output for channel number 0. Now this is the channel number 1, that is 500 hertz. Please have snapshot.
Channel number 1 output 500 hertz. Channel number 2 output, that is 1 kilohertz. And at last, the output of the channel number 2, that is 2 kilohertz. So you can see that we have successfully reconstructed, and actually we can say we have able to explore, okay, our signals. Channel number 0, 1, 2, 3 we have successfully received at the receiver end, right, after the demultiplexing all the 4 signals. So that's all about your experiment number 5, है ना? 5. EDM, time division multiplexing. Okay, you know, you have the list. You can check the experiment number. And once again, please have a snapshot of this system setup. This is the board. This is DCL02 kit, Falcon DCL02 kit, which is having the multiplexer demultiplexer section. And this is the setup, circuit setup, system setup. Okay, experiment number 6 is the system setup. Please have a snapshot of this also. And this block diagram, if you have not taken the snapshot, please take the snapshot of this one. So that is all about the hardware communication lab today. We have completed the 3 experiments, right? We have started with this particular kit for 2nd order and 4th order Butterworth low pass filter, right? 2nd order 4th order low pass Butterworth filter. And application of this one we have seen there in the sampling circuit to reconstruct the signal, right? So we have the sample and hold circuit that also we have done today. And at last, we have done the EDM, the time division multiplexing, right? So if you have anything to discuss, please ask. Neela ma'am, are you here?